1.4.1. The 5 uniform acceleration equations. The motion of an object moving with constant velocity is described by 3 variables and only 1 equation. The key variables for constant motion, constant velocity, are v, which is the symbol for velocity, unit is meters per second, d, which is the symbol for displacement, with the unit meters, and t, which is a symbol for time with the unit seconds. The equation for constant velocity is v equals d over t. This is the only equation that you can use if an object is moving with constant velocity. The motion of an object with constant acceleration is described by 5 variables. And unlike constant velocity, constant acceleration has 5 equations that will work for it. You can use any one of 5 equations if an object is moving with constant speed. The 5 variables that we use are Vf, which is final velocity in meters per second, Vi, which is initial velocity in meters per second, d, which is displacement in meters per second, or in meters, and a, which is acceleration in meters per second squared. T, time, is in seconds. The 5 uniform acceleration equations are equation 1, A equals Vf minus Vi over t. For this formula, we say d is dc. dc stands for we don't care. Because d is not in the formula, we don't care about it. This is going to be important a little bit later. The second formula is Vf squared equals Vi squared plus 2AD, where time equals don't care. The third equation is d equals Vit plus 1/2 AT squared. And in this case, Vf is the one we don't care about. The fourth equation is d equals Vft minus 1/2 AT squared, where Vi is the one we don't care about. And finally, the fifth equation is d equals Vf plus Vi over 2 times t. And this formula doesn't have acceleration in it, so we don't care. It's still a uniform acceleration equation, though, because it has 2 speeds, Vf and Vi. You can tell which formula is the right one to use for a problem. By deciding which variable the problem doesn't use. This is the variable that we labeled DC when we wrote out the equations, or don't care. Here's an example that shows you how this works. A car is moving north at 30 meters per second when the light turns red. If it has an acceleration of 8 meters per second south, how far does the car travel? A big step in figuring out which formula we need to use is writing out our list. VI is 30 meters per second to the north. This is positive 30 meters per second because north is a positive direction. VF equals 0. This is because the car is stopping at a red light. Stopping means 0 meters per second. The acceleration is 8.00 meters per second to the south, which is negative 8.00 meters per second. Displacement is our unknown, and t is the variable we don't care about. It's not mentioned in the problem at all. Because t is dc, we use formula number 2, which doesn't include time in it at all. Formula number 2 is Vf squared equals Vi squared plus 2AD. We can rearrange this for D. D equals Vf squared minus Vi squared over 2A. We can substitute in our values of 0 squared minus positive 30.0 squared divided by 2 times negative 8.00. This gives us a displacement equal to 56.3 meters. Since this is positive, we rewrite this as 56.3 meters to the north. Here's another example. Ben is waiting at a stoplight. When it turns green, he accelerates at 6 meters per second squared forward for 4.10 seconds. How far does he travel in this time? We start by making our list. Vi equals 0 meters per second. This is because he is not moving when he is stopped for the red light. The acceleration is 6 meters per second squared forward. Time is 4.10 seconds, and we're looking for displacement. Since it's not listed in the problem, VF is don't care, and this tells us that we should use formula number 3, because formula number 3 doesn't include the variable VF. This formula is D equals VIT plus 1/2 AT squared. And it doesn't need to be rearranged since displacement is already the variable in front of the equal sign. We can substitute in our values of displacement equals 0 times 4.1 plus 1/2 6 times 4.1 squared. This gives us a displacement equal to 50.3 meters forward.